Assalamu alaikum. So in this video we will generate a white noise and then we will make an auto correlation of white noise and we will see an interesting thing. It looks like a delta function of auto correlation of white noise. Then we will analyze why this looks like delta. Okay, so let's start. So first of all, let's take a very large number and then specify the time index, and then I have generated white noise by rand n function. So rand means random, it will generate this. Rand means random, this will generate a random numbers, and n means the standard normal distribution. That means if you take the mean or average of that white noise, all the values, then you will get 0 and you will get standard deviation 1. So this is actually the white noise. And now if you try to plot this white noise, you will see something like this. Okay, now we are going to make an auto correlation of that white noise. Let's see how can we do this. So we know that cross correlation function rxy looks like n is equal to minus infinity to plus infinity. This is cross correlation. Okay, so xn then y n minus l. But as we are try to finding auto correlation function, that means we are correlating a signal with itself. That means we have to take x twice. Oh, this is function of L. Okay, this is function of L. So if I make an auto correlation, the function will be looks like this. Here you have to write x, and again you have to write here x. And if you are trying to auto correlation with white noise, ACF of white noise, let's say the white noise is W, then you have to write W twice in this formula. So here you have to write Wn, then again Wn minus L. Okay, but we don't need this rigorous formula because we have a built-in function in the MATLAB which is x correlation, and if you have to just pass this W twice in this correlation function, and you will get the ACF or correlation function and 1L. Okay, so let's go to our code. So you see this is, so in this line we have used this x core, we have passed this white noise twice, and why I have written biased, let me omit this thing and then I will tell you why I have written this biased. Okay, now let's plot this autocorrelation function and let's see what happens. Okay, so you see I get a huge spike here, and the spike's value is, it occurs when L is equal to 0. Remember that we are plotting in respect to L. So now at the x-axis I have L, at the x-axis I have L, and when L is 0, you see a very large number, right? Now let's do one thing. Now let's write here biased, then all the value will be normalized. That means from 0 to 1. So if okay, so now you can see that this value has become 1 or quite similar to 1, and these values are so small. These values are so small. In this point this value is so small, tends to 0. This value is also so small, quite similar to 0. That means this function looks like delta, right? Now let's talk why this function looks like delta. That means the autocorrelation of this function white noise looks like delta. So I have a white noise, and the same white noise here I have made this picture some transparent. Can you see this picture? I have made this picture transparent, and the formula for the autocorrelation of white noise looks like this. And let's first take L is equal to 0. Okay, So if I take L is equal to 0 and then I do this multiplication, then I will, let's say it is the R versus L graph. This is the R versus L graph, and at 0 let's try to find what will be the value at 0. Okay, and to do this, you see that Wn and Wn minus 1 both are same. That means I have to put this value here. Okay, put this value here, and you see all the values matches with itself. That means here you can see the both values are positive, and if multiply this you will have positive. Then you will see that the both signals, I mean Wn and Wn minus 0, both are negative here, right? So if you multiply negative and negative, you will get positive. Similarly, you will get positive here because both the signals are positive here and both the signals are negative here. So multiply two negative will give you positive. So you will get many positive numbers here, and then if you sum those positive numbers, then you will get a very high value. And then if you normalize this high value, this value will be 1. So it looks like a delta function. Okay, now let's see when L is equal to 1. So when L is equal to 1, that means we are now trying to finding the value at this position. When L is equal to 1, let's try to find what is the value of R. So to do this, I just need to shift this picture. Okay, so let's shift this picture to the right. Okay, so I have shifted this picture because Wn minus 1 means I have to shift this picture to the right. Now you can see that, okay, I think the shifting is not so good. Okay, now let's see. Now you can see that here both the signals are positive. Then you will get, if you multiply, then you will get positive. But here one is positive but one is negative, so if you multiply you will get negative. Then again here one positive one negative, you will get negative. But here you have both the signals are positive, then you will get positive here. Is there any both negative? Yes, here you have both the signals negative, then you will get a positive here because both negative and negative multiplication of that signal gives you positive. And then if you sum all the values, some is positive and some is negative, so positive and negative will cancel out and you will get a very small value. Okay, and that's why here you get a so small value. Here. Okay, so if you do the same thing for L is equal to 2, after shifting it you will see the same thing. L is equal to 3, you will get the same thing. L is equal to -1, -2, -3, you will get the same thing. Okay, and that's why you get a autocorrelation functions looks like delta, and it's only for white noise. Okay, so thank you.